Thanks everyone for being here. My name is Daniel Golden. I'm the Director of Machine Learning at Arterys. We're a San Francisco-based startup that's focused on using a combination of cloud computation and artificial intelligence to make radiology faster and more accurate. And our offices are just in Soma, about a mile away from here, so it's a short bike for me. Today I'm going to be talking about some work that is not in our product. We have some products that are out right now, which I'll explain briefly. I'm going to be talking a little bit more about some research that we've been doing on decision support for radiologists, specifically for radiology involving lung nodule screening. So that's screening for lung cancer using computed tomography. And so the title of the talk is a deep learning-based intelligent reference library for lung cancer decision support. And decision support is a little bit different from straight-up classification, segmentation, detection, in that it aims to provide utilities to doctors to help them make their own decisions as opposed to making the decisions for them. And I'll get into some more detail as we go through. All right, so Arterys has been around as a company in some form or other for about 5 years, and in that time we've had a few things that we like to think of as breakthroughs. We were the first company to introduce a new kind of cardiac MRI to the radiology community called 40-flow MRI, which is for cardiac imaging, which is a method of acquiring both anatomy data and blood flow information simultaneously. And then we were leveraging AWS and GPU instances available there to visualize that data in high dimensions. It's a four-dimensional data set that has a time component to it, so it requires some 3D rendering capabilities. We were the first company in early 2017 to receive FDA clearance for a cloud-based deep learning product for a medical product. And that was for our segmentation model, which is in our cardiac application, for automatically segmenting in 3 dimensions the volume or the ventricles of the heart. We were the first company to have a solution that maximally enables the protection of patient privacy for a cloud-based medical solution like what we are. So how that works is we actually install a server within the hospitals, and that server holds all of the PHI, or protected health information. And that data is then sent to the browser of the client, wherever they are, when they connect to their hospital, and they simultaneously make a connection to AWS, our servers. So we are serving up the application interface and the medical data, the pixel data and the visualizations, and then their hospital is serving up the patient information. So we never actually store the patient information on our servers. And this is a way that not only reduces our reliability, but increases trust from the clinical partners that we work with. And then earlier this year, we also got FDA clearance for a broad oncology solution, which allows for deep learning-based, or in general machine learning-based segmentation of lesions in the lung and liver and other solid tumors in the body. And we're using that to develop products right now for the lung and liver. So just a few numbers to describe Arterys. We have processed over 30,000 patient cases on our system. That is primarily through our cardiac product. We have over 200 active clinicians working with our system, spread across over 100 hospitals. Our cardiac product is regulated in over 28 countries around the world, and we've received 5 FDA Class II clearances. We have 3 offices in San Francisco, Calgary, and Paris, and there are about 80 employees spread across those offices. Our headquarters is in San Francisco. We have distribution partnerships with 2 out of the 3 major OEMs. That's Siemens and GE, who are still working on Philips. And we've received to date about $45 million in venture funding. So we have 3 main products right now that are cleared and shipping to customers. The first is our cardiac product, Cardio AI, which covers many different aspects of cardiac MR, which can assess diseases like heart failure, problems with the valves of the heart, congenital defects, and others. And then our lung and liver products, which are focused specifically on cancer and solid tumors. And all of these are FDA cleared in the US. So I'm going to be focusing on, again, a specific research project that we've been working on, which we call a lung nodule intelligent reference library. So I want to just put a disclaimer here. We do have some clinical products for sale right now. However, what I'm going to be discussing, the bulk of this, is not in our clinical products. It's still in research. So it's not yet cleared for clinical use, although we hope to clear it in the near future. Some of the technologies that I'm going to be describing are actually in our FDA cleared products, and I'll call those out explicitly when I get there. So lung cancer is a major public health hazard. Among cancers in the US, these numbers are for the US only, it actually is more fatal than the next 3 most fatal cancers combined. That's colon cancer, pancreatic cancer, and breast cancer. So it is by far the most fatal cancer in the US. But there's a silver lining there, which is that screening, specifically via low-dose computed tomography, or CT, does save lives. And that's the conclusion of the National Lung Screening Trial, which concluded about 5 years ago, which showed that when compared to conventional radiograph screening, that's two-dimensional planar X-rays, low-dose CT screening, which is a volumetric acquisition, actually shows a statistically significant reduction in mortality for lung cancer. So this doesn't just find more cancers, but it actually reduces mortality. And that's why in the US, low-dose screening via computed tomography is now recommended for high-risk patients. And then these guidelines are also being followed in Europe and in other countries, based on trials like the NLST trial and other similar trials in Europe. With that said, although screening does conclusively save lives, it has a lot of challenges associated with it as well. The first is that it's time-consuming. For an exam which does not have any nodules found, it might take a radiologist about 3 minutes. But if there are nodules found, and often they're benign nodules, counting, characterizing, measuring, et cetera, doing all of these things with the nodules and then creating a report, which is usually sent to the referring clinician, can take a lot of time, 10 or more minutes if there are actionable nodules that require follow-up. Actually performing the screening, what the radiologists do in their workflows, is very challenging. Nodules are very small. I'll show some examples of this later in the talk. And they look very similar when looking in 2 dimensions to blood vessels within the lungs, so normal anatomy. And in addition, especially if the nodules are abutting other structures in the body, such as the pleura in the middle of the chest or the chest wall on the periphery, they can very easily be missed because they are iso-intense. They have the same intensity, the same brightness as the surrounding normal tissue. And finally, the method by which low-dose CT screening actually saves lives is by detecting cancers, which are almost always confirmed via biopsy afterwards. But the problem is, as more people get screening, there are more biopsies performed, and so if the screening is not very effective at finding malignant nodules, there are a lot of people who are receiving biopsies unnecessarily, biopsies which then are shown under histopathology, the examination of the slides, to be benign, not malignant, not dangerous to the health, and patients who receive those biopsies are really not benefiting at all from those biopsies, which usually involve some sort of a fine needle that is used to extract tissue from the lungs. And biopsies have complications associated with them as well. It's not just discomfort, but they put patients, especially sick patients who might have other comorbidities, at risk for other diseases such as collapsed lung or other issues or infection. So we really want to reduce biopsies to only those patients who would benefit from them. This is just an example from a follow-up study that uses data from the National Lung Screening Trial, where this is showing how effective current screening is. So on the y-axis, you have different what are called the lung RADS categories. This is a standardized reporting system where when a radiologist reviews a lung CT screening study, they will assess it as having a certain likelihood of malignancy, where a lung RADS category of 1 near the top here means low likelihood of malignancy, and a category of 4A, 4B, or 4X, which are the highest numbers, are high probability of malignancy. And that's as high as the chart goes, is up to 4B. And 4X means something that's a little bit different, so I'll focus on 4B as the top. And what this chart is showing is that for those lung nodules that have the highest likelihood of malignancy from radiologists, experienced radiologists, on the far right-hand column over there, after biopsy, only 34% of those were shown to actually be malignant, to actually be cancer, which means that 2/3 of all biopsies performed on the most malignant appearing nodules were actually of benign nodules that eventually, in retrospect, were unnecessary. So we really do want to reduce the number of unnecessary biopsies here. So to address the many different complications of low-dose CT screening for lung cancer, including the problem of having too many unnecessary biopsies, we have an approach that has 4 different steps. There's actually 3 different major steps. Steps 1 and 2 go together, which I'll explain. So steps 1 and 2 are 2 different deep learning-based models that are for lung nodule detection, automatically finding nodules in low-dose CT scans. The first model, number one, is a proposer, which sort of overzealously proposes potential nodules, and then this is followed by a classifier that reduces the number of false positives output from the proposer. And I'll get into all these in a little more detail in subsequent slides. The third step after the lung nodule detection step is volumetric segmentation. We use a deep learning model to segment nodules, which allows us to characterize them, both the size and then also distribution of pixel intensities within that nodule, such as the average intensity, which is relevant for prognosis and likelihood of malignancy and other things, as well as the shape of the nodules. And then the fourth step, which is really kind of the focus of this talk, is similar image retrieval. This is given a nodule that the radiologist is considering right now, show some similar nodules as well as their biopsy-confirmed outcomes to help the radiologist make a good decision about the likelihood of malignancy for the nodule that they're looking at right now. So then they're not just using the information in their head and from their training, but they're also using a large database of similar nodules in order to characterize that malignancy. So I'll go through these in a little bit more detail. So all the models that I'll be describing here are trained on this one open data set called the LIDC IDRI data set. It's an open data set with a little bit over 1,000 different CT scans, each of which was reviewed by 4 expert annotators who both detected and segmented volumetrically nodules within them. There are a little over 1,300 nodules. Some patients had more than one nodule. Some patients had no nodules. And we do a standard split where 80% of the data is used for training, 10% for validation, which is part of the training procedure, and then 10% for test. Sure.
So the data is labeled by the humans saying, here's a nodule, and then do you have the labels on if that nodule was biopsied and got cancer or not?
Sure, I'll repeat this in case it doesn't come through in the recordings. The question is, we have labels for where the nodules are and their segmentations. Do we have labels for their biopsy-confirmed outcomes? So anything that happened after that scan was acquired, and the answer is no. In this data set, the labels are created solely based on the image content. For this data set, the patients were not followed up to confirm malignancy.
Are they realistic image content? Or
These are, so the question is, are the images realistic?
real patients?
Yes. So this data set, this is, again, it's an open data set. It's on the Cancer Imaging Archive, a government-funded website. So you can learn much more about it if you're interested. But these are scans that were collected retrospectively for this data set, and they're collected from scans that were used for standard clinical care at several different institutions. Sure.
What is the format of the images?
So these are CT scans. They're volumetric. They're in a standard medical format called DICOM. Don't ask me to tell you what that stands for. It's an acronym. But for radiology, it's the very well-established standard for how images are stored.
So 3-dimensional volumetric DICOM images?
That's right. Technically, the DICOM images are 2-dimensional, and then there's a series of them per study, but yeah. And I think we'll have plenty of time also at the end for questions. I'm happy to be interrupted in the middle. That's no problem, but we'll also have time at the end. OK. So stage 1, again, this is the first of 2 stages of our lung nodule detection network. This is a nodule proposal network. Again, the goal is to find as many nodules as possible, possibly including some false positives. So some technical details. This is a 2D UNet-based segmentation network. As input for any given slice, it's trying to detect via segmentation nodules on that slice. It takes as input that slice and a few surrounding slices as well, packed together as channels into the input of the network. The output of this model is a segmentation mask, where the connected components of that segmentation mask, which is shown, is not super clear, but an output segmentation mask from the proposer network is shown in the bottom over here. And these are potential nodules where each connected component is one potential nodule. And in our preliminary results with this data set, we show that we have about 95% recall of nodules. And then stage 2 of that detection network is the false positive classifier. This is something we call a 2.5D network, where the nodules exist in 3 dimensions. The data is 3-dimensional. But to save memory and compute time and reduce overfitting, we actually take 9 slices distributed in solid angle through that 3-dimensional space. So then we end up with 9 2D slices. And then we pack those together as channels as input into a ResNet-based classifier. And again, the purpose of this network is to reduce the number of false positives from the previous stage. And in our preliminary results, we find that when you combine stages 1 and 2 together, we have about 92% recall of nodules at 2 false positives per scan, which is a pretty standard way of reporting these results. So the third stage is volumetric segmentation of the nodules. In this case, we actually have a three-dimensional network, which takes as input a three-dimensional patch from the original CT image. We know the center of the nodules from the previous stage, so it takes in a patch centered at the nodules. And then we use a network called eNet, which is similar to UNet in that it's a semantic segmentation network, but it has a lot of optimizations to reduce the computational complexity and memory requirements. And this allows us to take larger input patches or use larger batch sizes and so on during training. And this model for segmentation actually is in our FDA-cleared product. And in results that we showed to the FDA that were reviewed, we find that we actually have an error in volume error comparable to expert radiologists from that LIDC IDRI dataset, where we actually compared our error to the standard deviation of errors that we were getting from that data set from the 4 different annotators. So I want to sort of emphasize the fact that we get results that are similar to an expert annotator with sort of a fun little Turing test that I'm going to present to the audience here. So what you see here are 3 rows, 5 columns. This is all the same nodule. Each of the rows is a different slice through that same nodule. Each of the columns is a different annotator. One of them is our model. 4 of them are the expert annotators from LIDC IDRI. And I'm showing the segmentations here that each of those annotators provided, again, one of which is our model. And this is data from the test set, so it wasn't used for training. And the first thing you might notice here, especially on that first slice, is there's a lot of variability in how the annotators perform these annotations, and there are a few reasons. Number one is that different annotators have different levels of experience, different impressions of what constitutes a nodule. And number two, annotators sometimes use semi-automated tools like flood filling tools, where they click once and it sort of expands the segmentation region in a certain way. And they have different levels of how much they trust that tool, how much they error check, and so on. And again, although these annotations were collected to form this database, they're probably very similar to how these annotations would be made clinically. So the fact that annotators may not have checked how their flood fill tool is working for this data set is probably representative of how it works clinically. So my question to the audience is, for each of these columns, which one do you think is the model as opposed to an actual human annotator? And I'm just going to go and do a show of hands. How many people think A is the model? A few. How many people think B is the model? And I'm sorry, I'm going to stop in just a second. There's no annotation in C because that annotator, be it the model or the human, thought that this was not a nodule. OK, with that said, let's do it again, just in case anyone changes their answer. A? OK, about the same. B? C? D? And E? I would say it's a solid tie for B and D, and then E has a little bit more than A. A is the least. Very few people voted for C. The answer is A. This is our model. And sort of the take-home message, I probably wouldn't have chosen this example if it was going to be really easy. So sorry about that. But the take-home message here is that there's a lot of variability in expert annotators. And when a model actually looks like statistically as good as an expert annotator, then like in actual examples, it can really mirror what the expert annotators are doing. All right, on to the main theme of this talk again, which is similar nodule retrieval. That's stage 4 of those 4 stages from the previous slide. So similar nodule retrieval, again, is a tool that we use to help radiologists make decisions about the likelihood of malignancy of the nodules that they're examining. So this is a form of content-based image retrieval, or CBIR, if you've heard that before. And the main idea is in some high-dimensional feature space, we look for neighbors that are close in that high-dimensional feature space to the nodule that's under question. That high-dimensional feature space is made up primarily of features that we extract from the false positive classifier, stage 2, that I showed from before, where that classifier has an output that's really just true or false about whether the nodule is a true nodule or not. But if we remove that last layer and take the second to last or penultimate layer, we have about 1,000 sort of internal deep learning features. And those are the features that make up this high-dimensional feature space. And this is sort of a proof of concept, and there are many other ways one could use those features. This is sort of the initial thing that we did, and it actually works pretty well in practice. We combine those 1,000 or so features with some features we've directly measured from the segmentation network, which are nodule size, which comes right out of the segmentation, average intensity, which is used when you look at the pixels within that segmentation mask, and some other things. Sorry, I should say that this image right here is just showing a given query nodule, which is in the middle, the nodule of interest, and then a t-SNE collapsation of the 1,000 or so features into 2 dimensions, just so you can see like which nodules the model might interpret as similar to the query nodule. Okay, so I'm going to explain just real quickly in a block diagram how the training system, the retrieval system is trained, and then how inference works. So initially you have a database of training images, which again are from LIDC IDRI. Train a classifier to say which nodules are true or false. This is actually the output of the proposal network, and then you end up with a trained classifier. From that, we then have a nodule image database, which are nodules for which we know the biopsy-proven outcomes. From those, we use that trained classifier to extract features, again, from the second to last layer. We also use, I guess I don't show this here, but we extract some features from the segmentation network as well. And then from there, we have a database of nodules and their features. So we have the nodule pixel data that we used for the feature extraction, as well as the 1,000 or so extracted features, which we're going to use to calculate similarity.
So that's a binary classifier?
The classifier as a whole has many stages, hence deep learning, and the last layer is binary. But we actually, when we train it, we use that last layer, the binary true-false. But then for the feature extraction step, we remove that last layer and take the 1,000 features from the previous layer. Okay. So once we have the nodule feature database, this is how inference is run when a radiologist actually uses our application and wants to get these similar retrieved nodules. So the user has a query nodule they're looking at, and then they'll click on it or some other way, indicate that they want these results, and we'll use that trained classifier to extract features the same way we built up the database, but now to extract features from the query nodule. We'll use those features, and then using some sort of mean squared or equivalent method, calculate similarity between those features and the features in our database via some sort of nearest neighbors type algorithm, and then retrieve the most similar nodules from the database, as well as the images, and then show those images to the user, along with some measure of the similarity, as well as the biopsy-proven outcomes for those nodules. And now, I'm going to take a big risk for any presentation and try to show you a live demo of this in action. So let's see if this works. All right, so this is actually our application. Again, it's a demo application, not our application that we show customers, with all this in action. So I'm going to open up a study right now in our application. This is all running on AWS. The CT is going to load in the middle here, and that is actually all being created and rendered on AWS live and then sent to the browser. This worked when I tried it earlier. I'm still feeling optimistic. There we go. OK, so this is the CT exam. What I can do is scroll through here. I'm going towards the feet of the patient now. Now I'm going towards the head of the patient. And what you're going to see, if I go slowly enough, in the lower right of this image is one of the nodules that was detected and segmented by these models. And I'll zoom in a little bit over there. So that's a nodule that went through those first 3 stages of the pipeline in the back end, where the nodules were detected with the proposal network and the classification network, and then segmented. And this segmentation is actually volumetric. So if I scroll real slow, you'll see segmentations on all the slices, which when put together constitute a volume. So we can get a little bit more information about this nodule. So if I click over there on the right-hand side, you can see a close-up view of the segmentation result in 2 dimensions here, as well as some parameters. I apologize for the size of this here. Let's see what happens if I press this. It got a little better. Some parameters determined from the segmentation and the pixel data, including the size of the nodule, diameter in 2 dimensions, and volume in milliliters, and then the average intensity in the standard CT unit of Hounsfield units, which is just the average pixel intensity here, where, again, the pixel intensity may be indicative of a certain level of malignancy. So I'm going to undo that. And then if I click over here in AI analysis, what you'll see are the CBIR results, the results of retrieving similar nodules from our database based on features extracted from the classifier. So over here on the left is the query nodule. Again, this is the nodule under study that the clinician is making a clinical decision about. And then on the bottom here are thumbnails of the most similar retrieved nodules from our database based on those 1,000 or so features I mentioned earlier. Over here, you can see a measure of the similarity of that retrieved nodule to the query nodule on a few different dimensions: size of the nodule, average intensity, and this AI score, which again is the 1,000 or so features from the deep learning classifier, as well as the biopsy results. In this case, the nodule was negative. It was biopsied and found to be benign, and that information is shown there. And this example here highlights not only that we have let's say this example highlights the utility of, instead of giving the radiologist the answer, but actually showing them similar nodules and letting them come to a conclusion. So in this case, the query nodule over here on the left has sort of a lobulated or lumpy appearance. It has some diffuse margins that are kind of blurring into the background. It has some large-scale inhomogeneities on the inside. And the similar nodule actually looks quite different. It has sharp edges. The inhomogeneities are at a much finer scale right here, and it's generally round in shape. So as a radiologist, I might look at that retrieved nodule and say, this is not actually very similar to the nodule I'm interested in. So the fact that it has a negative biopsy probably doesn't pertain much to the nodule that I'm considering right now. So I'm actually going to ignore it and go on to the next answer. And when I look at the next result, I actually see a nodule that has a very similar appearance. It's lobulated in appearance. It has diffuse margins. It has large-scale inhomogeneities on the interior. And in this case, the biopsy result was positive. This actually was biopsied and shown to be lung cancer. So with this result, I can see a nodule that's very similar, and I know that the biopsy result was positive for cancer. So that will make me increasingly suspicious that this nodule that I'm considering right now may also be malignant, and I would likely upgrade the lung RADS category and suggest a biopsy, for example. And the fact that the first return result doesn't look very good, the second return result does, means that we probably have a little bit of work to do on this similarity metric and so on. But nonetheless, I think it's a pretty good highlighting of the utility of showing the radiologist the information.
So this part will be done by physician.
So what I'm doing, all this clicking that I'm doing right now, would normally be part of a clinician's workflow that they would do on their own, yes.
It's not a part of the algorithm that would say, look at this, like that.
What the algorithm has done is, so there are hundreds, in this case of the demo, there are hundreds of there are hundreds of nodules in our database, and we have returned the top 10, and that selection of the top 10 is the deep learning part.
But I mean, this visualization, oh, this is not it, let me try that.
Yeah.
This is done manually by the
That's correct. Yep, exactly. I beg your pardon? Again, based on that similarity metric, those 1,000 or so features. So based on something like the root mean squared distance between the features calculated on the query nodule and the features calculated on the nodules within the database. So that's how you determine the top 10. The top 10 are those with the 10 shortest distances.
So the recommender system gave him,
Yes, exactly.
and he can use his knowledge and say,
Yep.
oh, this is good.
Yep, that's right. Go ahead.
Is there a reason to go with the similarity module rather than actually making the prediction?
There are a few reasons. Number one is radiologists have a lot of training, and like anybody with a lot of training, someone handing you the answer is sort of less appealing than you making a decision on your own. And beyond that, radiologists can incorporate a lot of information that's more challenging for a model to incorporate. So for example, they'll better know the patient history. They may have done a clinical exam that the model doesn't have information about. They may have additional information that they want to augment these results with, or really they would be augmenting their additional information with this tool, for example. And then additionally, you asked if there are regulatory implications, and absolutely there are. If you actually are returning a diagnosis as opposed to something like this to the radiologist, it's still probably a class 2 product, but it's designated by the FDA as CADX, so it's computer-aided diagnosis, and this typically requires a clinical trial or clinical assessment to prove safety and efficacy, which can be a very long process, and that's because you're taking away some of the decision-making ability from the doctor, whereas this doesn't really take anything away, it really just adds to it. And so it would have lower regulatory requirements. In addition to, again, the workflow I just went through, the visual comparison and looking at the biopsy results, we just have a tool over here that shows, of those top 10 most similar results, what fraction of them had biopsies that were malignant. So we would probably need to tone down this language for an actual FDA submission, but this is just a quick at-a-glance view of what fraction of the return results had biopsies that were malignant, or rather were proven to be malignant via biopsy. I'm going to go back into the slides. I just have a couple more. Any other quick questions about this workflow? I got it open? Go ahead.
Yeah, when you have biopsy, you only have pathology information. Is there a plan to put that in there?
Yeah, so there's a lot more that comes out of a biopsy than just positive or negative. Is that what you're getting at? Yeah, so there are many different subtypes of lung cancer. These can be determined based on histopathological examination of sections of the tissue under a microscope, or in a more modern way, via genomic or other molecular assessments of subtypes. And that would also be very valuable to put in here. Ultimately, it is very unlikely a patient would ever undergo treatment based on assessment by radiology alone. They would almost always have a biopsy. So most likely, any patient with malignant lesion or nodule would have a biopsy anyway, so you would get that information otherwise. It's not critical, but I think it would be helpful. Go ahead.
The image data has different resolutions. You rescale to get into a particular resolution.
Mm-hmm.
And have you found that has an impact on your predictive?
So the question is, how do we deal with images that have different resolutions? Because really, it's kind of institutional policy and operator or technologist policy about what resolution you do a given acquisition in, and also depends on the equipment and so on. So many of the images that we use for training and for validation have different resolutions, both resolutions in the XY plane and then also in the Z plane, so how far apart the slices are from each other. So we do use a common resolution. I'd be hard-pressed to say what that is. It's on the order of 1 millimeter per pixel, and we rescale all images to that common resolution, interpolating as needed. I do not think we have done I think we've done a few experiments to try different types of normalization like that, but not a full hyperparameter search, just because that rescaling is an extremely expensive operation. So we typically save all the reformatted data and then do hyperparameter search on model parameters, which are cheaper to do on the fly. But this way we did this rescaling is common in the literature, and it's something that works pretty well for us. Actually, I'm sorry that I don't know how much time I have left. It's 3:05. Maybe I have until 3:15. So maybe I've got 10 more minutes. So maybe I'll just polish off the slides, and then we'll do questions at the end, if that's all right. But I think we should have some time. I have very few more slides, which I'll breeze through. All right, so some quick implementation details. The inference for all three of these models, again, there's only 3 models because that similar image retrieval model uses the classifier model for all of its work. Take about 90 seconds with an NVIDIA P100 GPU. About half of that time is GPU time for detection, classification, and segmentation. And then 50% of that time is morphological operations, image warping, again, generally taking the images apart, stitching them back together, reformatting them to a common resolution, and so on. So the fact that we spend 50% of our time in the CPU suggests that we have some work that we can do to speed things up, possibly move some of that work to the GPU, and so on. So we're optimistic we can reduce that time more. But actually, all of these things can be done in pre-processing. Nodules can be detected in pre-processing, and then those detected nodules can be segmented and classified in pre-processing as well. So as soon as the data is uploaded to our servers, we process it, and then by the time the radiologist opens the study to view it, it's already done. So there's no actual waiting time for the models to run. So that works in our favor. Other implementation details, we use some standard distortions such as warping, like affine transformations, contrast, and brightness, and so on. We use some optimized loss functions to help focus the models on the nodules, because the nodules constitute, per pixel or voxel, it's on, I can't remember the exact number, but it's something like 0.01% of the image is a nodule, typically. So it's like extremely large class imbalance between background and foreground when looking at nodules. So we have to do some customization of the model's loss functions to help them focus and start learning. And we do random search for hyperparameter optimization, primarily hyperparameters related to distortions and model network parameters. So those are all my content slides. I want to thank very much my team at Arterys, who's worked and done most of the work on this. That's Sean, Jesse, Felix, Matt, as well as the curators of the LIDC IDRI dataset and the NLST dataset, which I didn't talk much about, but the examples in the demo actually come from the NLST dataset, which is a dataset that's also open and free, as well as our clinical co-founder, Albert, who helped a lot in the conception and curation of this research project. And that's all I have. So I'm Dan again. My email address is easy to remember, dan@arterys.com. I love email. If you just want to chat, that's great. If you're interested in any of our open positions, interns, product management, project management, happy to talk about that, but don't hesitate to reach out. Thank you very much. Yeah. So the question was about the flow of like how the data actually gets acquired and flows through the hospital, flows through our system, how it's actually read. Typically, what will happen is we'll have this system that's installed in the hospital, which we call the PHI service, whose main purpose is to remove identifying information from the images before they get sent to our servers, but also it works as an interface between our system and the hospital systems. So the referring clinician, like primary clinician, will suggest a lung CT exam. The patient will come into the hospital. They'll be scanned by a technologist, not a radiologist. And then the data from the scanner will be sent to our PHI service and then to our cloud, again with protected health information stripped out. And then at some point later, it could be the same day, it could be days later, the radiologist will log into our system online, because it's all web-based, and review the scans and make assessments, and then send the report back to the referring clinician with the results. So that's like the whole workflow, if I didn't miss anything.
In the meantime, from what is shown on your website, how is it helping radiologists? Or what is
So the web client is actually is a viewer, as well as it has these measurement tools, these artificial intelligence augmented measurement tools and so on. And the radiologist will use our application to view the scans. So this is how they actually read the study. They scroll through, they reformat the images, they look for nodules, for example, and they'll also use these tools which show graphical overlays for automatically detected and segmented nodules.
does it also tell that we found a nodule in this image?
Yeah. So again, the interface I was showing over here is sort of a demo interface, but they'll see. I went to the wrong screen. Sorry. This is like the work list, the list of studies, and they would see something like this, where on the right is the list of detected nodules, and they could click on them to get more information. Does that answer your question? Okay. Go ahead.
So the example you showed are is the solitary lung nodule, which are the easier cases
Mm-hmm.
in the field. What is about the classifier accuracy when this is small metastatic?
Sure. This application actually does not support lung metastases, where those are cancers that have originated in another organ and have metastasized to the lung. That's not in our indications for use, just because that's a very broad and complicated thing to assess for all the different cancers. So our indications are actually only for lung cancer screening, incidentally detected lung nodules for scans that were required for some other purpose, such as some other interstitial lung disease, as well as follow-up of known lung nodules. So we don't support metastases right now. It's likely that our software works on those, but we haven't fully assessed it. And maybe what's also interesting are the difference between solid-looking nodules and ground glass nodules, or nodules that are very faint. I don't know. I could talk to that if you're interested, but the direct answer to your question for metastases is that we don't officially support them right now. Go ahead.
Did you do any of your own labeling of data set, or did you just work with the labels of
For this particular project, we only use labels that were already. Let me back up for a second. Is that true? Yes. For this particular project, we only use labels that were already assessed by the radiologists who curated these data sets. We have a lot of other projects we're working on simultaneously, so we do some of our own labeling.
how many, what's the rate of the useful images that you've seen in this data set? Are all of them good?
So this is a curated open data set, so the images are all pretty good. There are a few. There's some variability in different dimensions. There are some with very thick slices or large distances between slices, so we typically have poorer performance on those, but those are uncommon clinically. But overall, the images are all usable.
What's the average slice thickness that you get?
Wow. Geez, I'm not going to be able to remember that one off the top of my head. I think it's on the order of a few millimeters, but I don't remember.
5 or is it like 7 to 10?
I'm going to guess it's slower than that, but again, this is an open data set, so you can always just check it out online as well.
How's the performance for other organs?
So this is a lung product. This is not indicated to work on any other organs. It is a CT product, so CT and MR are both very common for looking at oncology. So the only thing you'd care about is what happens in a CT exam, and we haven't tested it, so I don't know. The lungs are unique in that in most cases, nodules are bright on a dark background, and that's because lungs are primarily air. So that would be very uncommon for most other organs. So I would expect that this particular set of models would not work well in other organs.
What's the accuracy
So content-based image retrieval doesn't really have an accuracy. There's a subjective thing about what constitutes similarity. The accuracy of the other models, the detection and segmentation, I mentioned in some of the previous slides. Detection is 92% recall with 2 false positives per scan. 92, yep. And then the segmentation was, it was as good as an expert annotator. I don't recall the actual volume error, but on the order of what's done clinically. Go ahead.
You made all your models on open data sets, publicly available data sets.
For this project, yes, that's right.
Do you also like the hospital, the radiologist work with you? Do they annotate the CT images, diagnose images for you?
Yeah, that's a great question. So I don't know if anyone's keeping time on this. I have it about 3:15. Maybe that's, does this end at 3:15? Okay, great. So okay, thank you. Okay, so I'll answer this last question. So we get, for different projects, we get annotations from many different places, and sometimes we do ask clinical partners or other radiology firms to perform annotations prospectively on data that we've gathered retrospectively. Sometimes we're able to work with clinical partners to get annotations they've performed retrospectively, typically if they're doing those annotations for standard clinical care. Unfortunately, for oncology, it's very uncommon to actually annotate on the image as part of standard clinical care. Usually radiologists will just look at the images, write a report without actually annotating the images in a way that allows us to collect those annotations later. So for oncology, we usually have to get our own annotations, except if there's an open data set like this one. For some other projects, we're able to leverage annotations that have already been made. This particular data set, the LIDC IDRI data set, is open. If you Google that, you'll find it. You can download it today. Yeah. We used a combination of public data and clinical data from clinical partners. Yeah.
I have one more question.
Okay. I'm going to allow other people to leave if you want to, because it's at the end of the time. But I'm happy to answer your question. Maybe I'll just hang up the mic now, and I don't know if people really want to hear me talk. I can keep it on, but maybe I'll hang it up and I'll be here for a few minutes afterwards if you have more questions.